the part we've been waiting for, the Flash Talks. Let's take it away. The first Flash Talk presentation will be about modeling stochastic systems with quantum algorithms, a new approach to epidemiological models. Suzieli, please introduce yourself and take it away.
Okay. Good morning, afternoon, or evening, everyone. First of all, a special thanks to you, Marlo, for inviting me for this flash talk. And I'm Suzieli Mendonça. You all can call me Suzy. I'm a PhD student from Brazil, and today I'll briefly showcase what we've been doing so far here regarding the modeling of stochastic systems in quantum algorithms when we propose a new approach to epidemiological systems. I studied medical physics in undergrad school, and nowadays I'm taking a graduation course in physics applied to medicine and biology at University of São Paulo in Ribeirão Preto. The picture is the entrance of the university. My research interests lie in the intersection of theoretical physics, biology, and quantum computing. Specifically, I work on developing mathematical models for stochastic biological processes, and I work exploring their implementation in quantum computing architectures. To do so, we first model the mathematical description of the problem. Let's say, for instance, a disease spread model. Then we write the Hamiltonian that describes the dynamics of this very problem in terms of quantum ladder operators. And next, we perform some transformations. So the Hamiltonian, we guarantee that the Hamiltonian is Hermitian and unitary, so we can simulate it in quantum computer simulators. We finally implement them later on quantum computing platforms. And in a very brief way, that's the project. If you want to connect to talk about it, I'm available on Discord where we can exchange LinkedIn profiles and emails. Okay, thank you.
Fantastic. Thank you, Suzieli. And then the next presentation will be given by Maria Dinka on characterization of time involution circuits by quantum process tomography on the IBM quantum computers. Maria, very curious. Please take it away.
Thank you very much, Marlou. Thanks everyone for sticking around. So my name is Maria, and right now I'm in between my master's and PhD in quantum algorithms at the University of Oxford. However, what I'm going to talk about today is a project that I've been working on for the past year with the University of Bonn and the Matter and Light for Quantum Computing Center in Germany. And the focus of my work was, as you said, on characterization of time evolution circuits. And the context for this is that, as everyone in the summer school is very well aware, current, even state-of-the-art quantum processors are severely limited by noise, which comes in all shapes and sizes, ranging from state preparation and measurement errors to crosstalk errors and even more. And one particular thing to notice about noise is that it increases with circuit depth. So the more operations we add to the circuit that cannot be executed in parallel, the longer the circuit takes to execute, and so the greater the chance that the qubit will spontaneously relax to its ground state and the information in its quantum state will be lost. And that's quite unfortunate because a lot of algorithms actually do require deep circuits in order to provide good solutions to the problems they're trying to solve. So there is generally a trade-off between the physical accuracy to which we are solving a problem with our quantum algorithm and the fidelity of the executed circuit with respect to the ideal one that we write on paper or in our code. And an example of that is time evolution, where the standard approach, the Trotter-Suzuki decomposition, gets better and better the deeper the circuit is. But a PhD student from my host group in Germany proposed a novel circuit, hopefully better, optimized based on the brick wall compressed architecture that we can see in the figure on the bottom right corner. And numerical simulations show that this was indeed better than the standard way, but there was a need for practical demonstration or real hardware. And so that's what I did. I implemented both circuits on the 5-qubit devices from IBM that were still available back last summer. And I compared and contrasted them using quantum process tomography methods to see how they really compare when we have noise around. Very briefly, what quantum process tomography does is that it centers around a map lambda, which maps the initial state of a system to the final state of the system, but we are not describing the system with a wave vector, rather with a density matrix rho to account for all the operations we do apply, as well as the noise that, or the operations that the environment unknowingly applies to the system. And with some mathematical manipulation, we see that we can describe this map by a matrix, Chi-Mn, which gives us all the information. So the quantum process tomography methods that I don't get to describe, they help us to compute this matrix. And now in the very final slide, we can see that what this matrix looks like. And if we flip quickly through the last slides, we see that the matrix gets worse and worse, it loses its structure as we add more and more layers to the trotterization, for example. So this is an example of how we really do the physical, even though we get more physical fidelity, the circuit fidelity decreases. So this is for 3 qubits, and we have plans to do this for 4 qubits. Thank you.
Amazing. Thank you, Maria. Great presentation. And can you guide us through those 4 last slides a little bit more? So we start here, 1 layer, 2 layers, 3, 4. What do we see?
Yes, so this is the Chi matrix that I was talking about, which showcases what this is the result of the process tomography. So this is the object of the methods that I implemented to compare and contrast. And what we see is that the more layers we add to a circuit, so initially, if we look at if we go one step before, it's an exact calculation, and we see that it's very well structured. We have some spots, a few bright spots, which is the operations that we really want to apply. So these are Pauli gates, essentially, on the 3 qubits. But the more layers we add on a real quantum computer, then we see that other spots in the matrix start to brighten up, because these are residual Paulis that the environment applies, meaning bit flips, phase flips, and so on. And comparing this for the 2 types of circuits, we can get a measure for how they actually behave and which one is more or less prone to errors. And we can do that, well, by eye, or we have we can define some fidelity measures to actually see a numerical comparison between these matrices at the same physical accuracy, for example.
Thank you very much. And I see more people typing on Discord, so please have a look there for more questions and comments. Next presentation will be by Erica on shining light on the photoexcited carrier dynamics and electronic properties of nanomaterials. Another topic which is very quantum and which we haven't discussed in this program so much. We've been focusing on quantum computing, and this goes more towards quantum materials and processes. So we're excited for your talk.
Hi everyone, thank you very much for the invitation for this talk. As Marlou said, this is a topic for understanding physical properties of nanomaterials. Actually, it is not only for quantum, it's actually to many fields. So I wanted to talk about how to understand electronic properties using Pomprov spectroscopy. The principle of this technique is very simple. You need 2 ultra-fast light sources. So these 2 beams, they will be called Pomp and probe. They will incide onto a sample. And by inducing an optical delay, you will be able to actually map what's happening before and after the photoexcitation. So you will be able to study all the processes on time. This information will depend very much on the probe frequency, so you will be able to access different processes. If you use X-ray, for example, you will be able, for a semiconductor, to see what's happening from the core to the valence band. Then if you use visible light, you will be able to track all the processes that happen from the valence to the conduction band and upper levels, like recombination, for example. And if it's to lower energies, you will be able to track the carrier dynamics, the motion of the electrons, so you will be learning about conductivity. In this slide, I just wanted to show how powerful and versatile this method is. These are not quantum examples, these are just different fields. On the left side, in this work, we studied 2D machines. So this is a kind of relatively new material. With Pomprov spectroscopy, we demonstrated that the material has a strong Kerr phonon scattering, which is not common in 2D materials, and also we prove slow heat dissipation. So basically what's happening is this material is converting almost 100% of the light to heat. And you can find applications that can be for plasmonic devices, but also on the biofield, such as photothermal therapy. On the right side, for example, we were studying a nanomaterial that was discovered 3 years ago. It's a titanium-based nanomaterial. So we actually gave like a first approximation of the band structure of this nanomaterial. This is a semiconductor with a 40 band gap, so it's a very wide band gap. But we found out that you actually can photoexcite it with just visible light, not UV at all. And these photoexcitations are very, very long-lived. So this actually makes this nanomaterial very promising for photocatalytic applications. And in general, bomb-prof spectroscopy gives you very rich information of electronic properties, so you can apply this in all fields in science, like for understanding quantum phenomena and chemical reaction and so on, electronic structure in general. So thank you very much.
Wonderful. Thank you very much, Erika. Very exciting topic. And we should talk. Maybe we can organize a virtual lab tour also, and you can show even more of what you're doing.
Sure, I will be happy to.
Thank you very much, Erika. And more questions on Discord. I already see a comment on use cases. The next thought will be by Adriano. Very excited for this topic on implementing QAOA for a job reassignment problem.
Hi everyone, thank you Marlou for this time. I'm going to talk about my currently bachelor's thesis that is implementing QAOA for a job reassignment problem. There you have like the little outline of this presentation. Well, I am a last year computer sciences bachelor student, and my director of thesis is Alejandro Matali, a quantum developer at IESA Enterprise, and also a particle physicist. First of all, we have to define this problem, the job reassignment problem, in which we have a couple of a set of agents that have their current job, and each job have the priority, and also each agent will have the affinity to the corresponding job. And suddenly, in the situation of the enterprise, it will appear a new set of jobs, probably with a bigger job priority, and now we have the situation of deciding if we have to do a reassignment of a particular agent to one of these new jobs. This situation could be formulated as a QO equation where we have it for each variable, which means that the particular agent will be reassigned or not to this new job, with the differences between the priority of the current and the vacancy job and the affinity from the current and the vacancy jobs, and the corresponding penalties that basically represent that no more than one agent could be on one job, and also no more than one job could be per agent. After defining the problem, we have the algorithm we're going to use, QAOA, that was previously explained in another exposition. Basically, we have the operational parameters, a quantum circuit that is parameterized by these parameters, and we will do a classical quantum loop of optimization of these parameters until we maximize the probability of measuring an optimal or suboptimal solution for this problem. For the implementation of this, we use OpenQAOA SDK. The complete workflow we have designed for doing this is in once we have first used OpenQA for the regular QA workflow, so as to get the icing cost over the optimized parameters and the initial parameters. And there we got a cost improvement over the theoretical quantum state. Then we will evaluate the initial, that is a non-reassignment configuration, and to get the initial configuration cost, and also compare it with the optimized configuration cost of the problem, so as to get like a more industrial cost improvement. For the real instance, this will be the cost one will show to a possible client. And after that, we will use a brute force solver for logical instances and get the optimal configuration cost, so as to get the approximation ratio of the optimized solution we get against the real optimal, the optimized solution of QA against the optimal solution from the brute force solver. And we have to implement this workflow and do the corresponding analysis for this. That's the complete project. Just for finishing my talk, it's like kind of an advertising time. If you're interested about trying OpenQA with zero extrapolation, you can scan that QR. We have recently helped in a pull request where we do that integration of Mythic certainly in the SDK. So just scan the QR and you can go to the tutorial of this module. Thank you very much for this time, Marlou.
Wonderful. Thank you for this great talk, Adriano. And congratulations on the micro grant by Unitary Fund with a
Thank you.
collaborator whom we are familiar with, Alberto Maldonado. How was
Yeah.
that for you, the comparison with classical models and how you see this in the future while quantum hardware is improving?
Well, for this job, we're doing a comparison with a classical solution, but it's more like a quantum-inspired solution with tensor networks. That is something that was programmed and implemented by Alejandro, my co-director, with his enterprise. They are currently having in production this kind of solutions. So for my thesis, we're going to compare how QA could perform against this quantum-inspired solution that it's quantum inspired, but it doesn't stop being like just classical computing. So that will be part of the analysis also. We haven't did that yet, but it's like the next step of the project.
Fantastic. Thank you very much. Here we go on quantum entanglement in curved spacetime. Joseph, please take it away. Excited for your talk.
Hello, everyone. My name is Joseph Izuma, and I'm presenting on quantum mechanics and curved spacetime. I've just recently finished my bachelor's in astrophysics at Baylor University in America, and I'm still an active member of my research group that I attended in undergrad called the Early Universe Cosmology and Strings Research Group. What I did in research is that I investigated a hypothetical effect called the Bose-Marletto and Verdral effect. And so it states that the quantum properties of a gravitational field, while though not directly observable, can actually be inferred by seeing how gravitational field affects the entanglement entropy of two particles. And so this is an indirect argument for the quantum nature of gravity, because in physics, there's been a long history of gravity and quantum mechanics being incompatible with each other just because of gravity. General relativity, Einstein's theory of gravity, models it as not as a force, but as a curvature of the fabric of spacetime. But quantum mechanics treats spacetime like we normally think of it. And so that's been the big problem between them. And so what I did is that I modeled two particles, an electron-positron pair, and send them on a trajectory towards the black hole and seeing how the black hole's gravity affect them. And so this little animation on the side is just their radial wave function as they get closer and closer. And right here, we're seeing probably an example of maybe it could be model collapse, because once something plunges into a black hole, that's where physics starts going into the realms of the unknown. But the conclusion is that what I did to measure their degree of entanglement as they went into the black hole was to plot their von Neumann entanglement entropy, which measures on a logarithmic scale the degree of entanglement between two particles. And so 1 will be when they're completely entangled, so a mixed state, and 0 will be when they're inseparable states. And so I use a periodic entanglement Hamiltonian for the classical non-gravity case. What I found for what I called Schwarzschild, which is just a spherical black hole, what I found for that case was that it completely took away that periodic waveform and then, in a sense, separated these states, because now as time goes on and on, these states are just with minimal entanglement entropy. And it must be mentioned that objections to the BMV approach still exist by notable leaders, and the study still is in its infancy. So,
wow, fantastic! This is really interesting. The next presentations will be given first by Saba, then by Yaman, and then Parsa. Saba, you will share your screen yourself. Please take it away. Go ahead.
Hello, everyone. I am Sabah Bospolat from Turkey, and I am a physicist and currently working as a scientist at Marmara University. I will talk about how to utilizing QML to optimize QA/UI ansatz, and I will specifically focus on the magnetic moment alignment problem. This problem can be thought as a subgroup of combinatorial optimization problems for simple cases, and the most famous COP is the max cut problem. In MaxCut problem, we are trying to find a coloring combination which maximizes the total number of edges connecting different colors. There may be many different coloring selections, as you can see here, but we are interested in the one with the maximum cut. And in simple cases, magnetic moment alignment problem can be treated as a max cut problem. And without any external magnetic field, the orientations of the magnetic moments are random, and the total magnetization of the material is approximately zero. But once we apply an external magnetic field, the magnetic moments come into order and they align with the field either in parallel or in anti-parallel. In this work, I focus on the magnetic materials, on the ferromagnetic materials. So the alignments should be in parallel with the external magnetic field and with each other. In quantum computation, we use QAUA to solve combinatorial optimization problems. In this algorithm, first you write your problem Hamiltonian using a QUBO or Ising model. In fact, these models are a part of Q-cobalt material, and I strongly recommend you to revise that material for the details. After that, you convert your problem Hamiltonian to a parameterized quantum ansatz, and next step is to run this circuit with randomized randomly initialized parameter set, and then you optimize these parameters using some classical optimizers. Therefore, QAUA is a hybrid algorithm, and for optimizing parts, we need classical computers. But recent developments in quantum machine learning opens a door to a fully quantum version of QAUA. And to this end, I changed the classical optimizer with a quantum feed-forward neural network and investigate a chain of ferromagnetic materials. I have to emphasize that as of now, we still need to use some classical components in this algorithm, even with QFFNN, but we are getting closer to eliminate these classical parts altogether. In the results, here you first see the results without an external magnetic field, and the plots show that as the length of the magnetic moment chain increases, the randomness in the individual moment orientations decreases, and the chain gains a net magnetization value as expected. And in the second figure here, you can see that the percentage error in the total magnetization value decreases with the external field in both directions. These are my preliminary results, and I'm currently working on to expand this study for some real ferromagnetic materials such as iron or cobalt chains, or maybe even monolayers grown on platinum substrates. Here are the references to check for further details, or you can get in touch with me whenever you want. Thank you for listening, and I can take questions now.
Fantastic. Thank you, Saba. And I saw it was like 6 slides, but I remember from your Flashtalk presentation in 2022 that you can make it within that time. Let me check if there are questions on the live channel. Yes, Adriano from Argentina asks, have you done some tests of how QML could react to local minima during optimization and compare it to classical optimization?
It's not, I mean, it's to be honest, it's worse than the process with classical optimization. But this is a problem about hyper-tuning the parameters, especially with the machine learning model. And I'm currently working on that part of the problem.
And Nigel asks, have you learned anything about the excited states of the electrons in your project?
No, this is just about the magnetic moment alignments. We are not, I mean, we have some excited states, but we get some excited states, but we don't want them. We are interested in the ground states, only the ground states.
Fantastic. Very exciting work, Saba. The next talk by Yaman. And Yaman created a quantum notebook based on the content that we are going through in the Womanium Global Quantum and AI program, which could be of use and help for all of you. Yaman, please share with us what you have created.
Hello, everyone. So this is probably less technical than the other projects and talks, but what I basically did is like I was trying to go through the quantum computing program, as we all have. And as Christina mentioned, it kind of like gets out of hand at some points, and like you get lost. So at that point, I decided like I'm gonna write everything down, because if you really want to know, if you understand something, then you have to try to teach it, or at least explain it in writing. So that's basically what I did. And in this notebook, I published it here at yamen-notebook.versal.app. So it's basically a static website with my notes on different topics from the QWorld workshops. Um, some of them are like from Q Bronze, Q Nickel, and I'm still writing Q Cobalt. I'm still not done with that. And what's like different about these notes is that I have some separation in them. So if you go to one of them, for example, Simon's algorithm, we can see that it's more math heavy, and we don't have any code basically in this note. And even some notes where I have code, it's just pseudocode. And that's actually intentional, because I wanted to create this separation between understanding the topic and understanding how to work with the framework. For example, like Qiskit and like Zerg and Classic, I wanted this separation between how like understanding how Simon's algorithm is implemented, and how it offers an advantage, and how to implement it using different frameworks. So that might be helpful to like some of you, like especially with coding backgrounds, because again, it creates this separation. You don't need to think about the functions, how it's written, the parameters you pass to the functions. You only need to think about the subject itself. And I might in the future add like more notes about how you can use these frameworks to implement these topics. So, and also in this notebook, I'm not gonna be like strictly sticking to quantum computing. I'm gonna be posting more notes. Some of these are probably gonna be about graph theory. I have some notes about graph theory when I studied graph theory, but they are not complete yet. So I'm still gonna work on them and then post them. Real quick, I'm gonna go over some frequently asked questions, and these are like, how do you write your notes? So I write my notes using Obsidian, which is a note-taking app, and then I hosted my notes using this framework on GitHub, Obsidian Digital Garden. It pairs really well with Obsidian, so I can easily share my notes here in Versal, which is a hosting service for static websites. And yeah, I think that's it.
Great work. This is really great and so useful for everyone. I also see comments on the Discord. Appreciation for Yaman's notebook. Amazing.
Thank
We will share it, your link, with QWorld as well. I think they would be very interested in working with you on this and sharing it in
That would
across
be, yeah.
further workshops. See more compliments. Very good initiative. More people typing. Thank you very much for sharing this, Yaman. And maybe people actually want to contribute and help, and you can expand it even more. Thank you
Yes,
for this
that would be
great
like
work.
amazing. That's one of like the topics in my notes. Is that like it's not strictly me. Like other people can join in and contribute to the notes. So yeah, that would be great.
Amazing. The next talk will be by Parsa Garavi on the AI as a project, empowering deaf individuals through AI, natural language processing, and image processing.
Hello everyone, I'm Parsa Garavi. I am currently studying biomedical engineering in Shaikh Beheshti University, Tehran, Iran. And I am here on behalf of ISA uh, to talk to you about the new solution for breaking the accessibility barrier of the hearing or DHL loss community. First of all, what is ISA? ISA is a non-profit social startup that aims to develop and introduce new technologies, features, and ideas to help deaf people and those with communication problems to communicate more effectively and efficiently. First of all, let me just give you a sense of the scale of the problem we're dealing with here. Right now, there are over 350 or 400 million people worldwide suffering from hearing loss problems. And it is estimated that this number will go up to 2.5 billion by the end of 2050. So according to our market research, we did some events and talks and gatherings in the past few years. And in these talks and surveys, we found out that 71% of people don't actually never used a technology-based solution for their communications, and 75% actually wanted to use, preferred to use modern technology. And actually, our solution, which is an app, in the next slide, has been accepted by almost 90% of the attendees. So what is our platform? Our platform is a comprehensive communication platform that has various services for people with communication problems, such as a sign language translator, speech to text, and text to speech. And also you can upload media to it to use these various kinds of features. And also there is a alpha version available on Google Play, so if you want to check it out. And if you could go to the next slide. And what values do we propose to you? First of all, we try to reduce inequality between communication and all classes of people. We try to increase accessibility to everyone and also try to promote educational justice. And here you can see various other things we do, like revenue streams, key activities, our key partners, and also what our target customers are. And last slide is our ways you can contact us. This is our website, and those are our our team members' LinkedIn profiles if you want to reach out, and we will extremely appreciate any help you can offer. Thank you.
Great initiative, Barsa. This is wonderful and really implementing the latest technology to make life better for people. I see people typing on the Discord already. Stay tuned for questions there. There are also people in our program who don't hear well or are deaf. And I expect that they would also love to be in touch with you.
Yeah, sure. Reach out anytime.
Fantastic. Thank you very much for your talk. The next presentation will be a double presentation by Ira Irianti and Mahia Mostafavi on the HHL algorithm with the Poisson solver for simulating density charge of 2D quantum dot arrays.
Thank you for this opportunity, and hello everyone. I hope you all have had a good day so far. My name is Mahia Mostafavi. I'm a master graduate in electrical engineering from Amir Kabir University of Technology or Tehran Polytechnic, and my dear teammate is Ira Irianti, and she is a graduate student in physics in Indonesia. And we're about to talk about the HHL algorithm with Poisson solver for simulation density charge of two-dimensional quantum dots array. I want to start with what motivates us. So the motivation is actually based on my master's thesis, in which I have to simulate and show the formation of two quantum dots inside a MOS structure, which is a metal oxide semiconductor structure, as you can see. And on the top level, I have 9 gates, and by applying different voltages on these gates, we managed to form a quantum dots at the interface of the silicon and oxide, as you can see in the picture. You can see that for that, I use MATLAB to implement and obtain my charge density distribution and potential distribution. So basically what I have done in MATLAB is that I solved Schrödinger equation and Poisson equation two-dimensionally. And I started from an initial matrix of my potential, as you can see on the left picture. And by having that, I solved Schrödinger equation using FDM and obtained a charge density matrix. And then by having this charge density matrix, we managed to solve Poisson equation, again using FDM, to obtain a more accurate and better potential distribution. So far, all the things have been classically, and the problem is that, as you can guess, it is very computationally intense and time demanding. I mean, my GPU almost burnt out during this modeling and extraction, because in FDM method, the size of our variable, the matrix size, is directly dependent on the number of grids and the value of meshing we consider. That's why I thought about a quantum approach to fasten this processor and this process. So if you could go to the next slide, we decided to use HHL algorithm, which is a quantum algorithm to fasten the solving of our Poisson equation. This method is rather new, but there are some works that has been done, but not with the exact example that we have here. So this is still undergoing, and we haven't extracted the results. We hopefully wanted to submit it as a Womanium project if possible. But as you can see on the top left of the picture, the Poisson equation is a second derivative of potential is equal to a constant like charge density. And we can consider this matrix as a linear matrix like A times X equals B. And by having this this linear matrix, we are able to actually implement the HHL algorithm to such a linear equation to obtain a better potential at the end. And hopefully Classic recently added a notebook for using HHL to solve 2D Poisson equation. And we're about to use that to obtain a more accurate plot for our density, charges, and our potential distribution. And thanks for your attention. If there's any question, I would be more than happy to answer.
Wonderful. Thank you very much, Maya and Ira. Very interesting work. There is such extensive research on this classically, but you usually need a supercomputer to really do the detailed calculations. And now, can we revolutionize this using quantum computing?
Thank you.
Ira, can you also share about your role in the project?
Sure. We start from the problem that Maya have. We want to see the quantum effect of quantum dot that Maya previously worked on MATLAB. We have this idea and bring it up to Womanium. Then eventually we get help from Classic community, and they assist us to use HTML algorithm, and yeah, there's other alternative on PKA and KPA that we can try also for the development of the study of quantum dots. So I try to from 1D Poisson solver move to 2D Poisson solver. We will use 2D quantum dot array. That this is challenging for us. Yeah. And
Fantastic.
for future prospect, we wish to explore more of this quantum effect, like maybe vortex, anti-vortex, or thermodynamics on it, like that.
Fantastic. Thank you very much for sharing, both Maya and Ira. And let's stay in touch about this, because it's very promising work and new to the whole quantum materials and semiconductor nanomaterials community. Thank you very much.
Thanks for having us, Marlou. I just wanted to say that we are more than welcome to cooperate with other groups. There are so many groups working on quantum dots and quantum nanoelectronics, and we would be happy to work with them. If they're interested, just DM us on Discord.
We will go Christina first. Could you, while I bring up your slides, introduce yourself?
Hello, everyone. My name is Christina Aredian. I am a PhD student here at Tennessee Technological University in Cookville. I am in my third year, and I teach design of algorithms and other fundamental classes. Sometimes classifiers get fooled by adversaries, and this is something that happens a lot. You think you have a good classifier, and all of a sudden you notice that your performance decreases sharply, and you don't know why. You may be the subject of an adversarial attack. What happens is, let's just take this image. We apply a small perturbation, and the result is going to be the image on the right, which, as you can see, you cannot perceive a difference. So you cannot say, hey, this one is really different from the one on the left. But your model, your machine learning model is going to give you a different label. And this example is not even as nice as others. For instance, if you have an image of a cat, it may come up that is a dog or something else, right? Something very obvious. This can create a lot of problems, especially with malware, so malware attacks, or no driver cars, right? So a car that doesn't have a driver is going to look for signage on the road. So let's say there is a stop sign, and there is an adversary that induces a perturbation. And instead of a stop sign, the machine is going to say, hey, this is a increase speed limit, right? So you can imagine what that can, what type of problems can be created. The same here with malwares. You have a detection system. You detect in your network traffic. You have a certain malware, and then you mitigate that with specific tools. So, for instance, the label on this, it's a GATAC. It's a type of malware that is treated with certain types of mitigation techniques. If instead the label change it to RAMNIT, you're going to try to mitigate with RAMNIT methods, which is not going to work for GATAC. Sorry. So basically, you are using resources and get nothing out of it. So that's why it's critical that your machine learning model is robust to this type of adversarial attacks. So what we do is just we improve the training with these added adversarial examples, right? So we teach the system how to recognize these tiny perturbations. If we want to make these systems better, of course, quantum computing can be of help because quantum machine learning models are in general more robust because they create a decision boundary that is spans across many dimensions, right? Instead of just two, it can detect entanglement and superposition. There are limitations related to the number of qubits that are being used. So right now, there is research work that is being done with images up to 100 qubits, so 10 by 10 in image. But we are hoping that the technology is going to help us build more rapid and more robust machine learning model to detect this type of attacks.
Great. Thank you very much, Christina. And everyone, please ask your questions on Discord to Christina to answer further. Stay on for the 3 last talks of today. The first one given by Abdullah Kazi on optimizing measurement-based quantum computation, MBQC, with graphics and tensor networks for VQE.
Hello, everyone. I'm Abdullah. And to talk about me, I was a participant for Womanium previously. And I think I did a lot of work with Womanium before this, and I've also worked with Classic. So yeah, so talking about my research project today, it's on optimizing measurement-based quantum computation with graphics and tensor networks for variational quantum eigensolver. Imagine you have a complex networks of coins where each coins represents a qubit. So the edges connecting these coins represents entanglement between qubits. So MBQC uses this entangled coins to perform quantum computation by flipping measuring each coin in a specific order. So what happens in MBQC? So in MBQC, there is some graph states and single qubit measurement. And in MBQC, qubits are represented as nodes in a graph, and the edges between them denote entanglement. Computational tasks are achieved through sequences of single qubit measurement, which is similar to flipping a coin to get head or tails. And this is also achieved through local operations on the entangled states, which is similar to manipulating each coin locally to achieve a global pattern. So when I'm using the term coin, it's an analogy to using coin over here. And talking about the graph state, a quantum state is prepared using local unitaries on a tensor product of Hadamard state, where E denotes the set of edges in the graph, and the graph state is crucial as it represents the entanglement structure that uses the MBQC computation. So talking about measurement calculus, if you can think it of a sequence of coin flip that can emulate any quantum network. Introduction to graphics library and what is MBQC optimization. So graphics is like a master coin organizer. So it is used to optimize and simulate MBQC on local Clifford decorated graphs. It's basically a library. So the purpose of graphic is to optimize the layout and simulation of MBQC to make computation more efficient. And the features are it pre-processes poly measurement to simplify computational complexity, like sorting different qubits to make them more easier to flip in the right order. And there is also some more optimization strategies, like there is order measurement commands to simplify the sequence of quantum operations. And also it adjusts the measurement of signals to minimize interdependency, similar to ensuring each qubit flip is independent to the others. And it also has some complexity, pattern standardization complexity, which is O raised to n raised to 3 due to commutation relation within the pattern. And also typically O raised to n raised to 5, focusing on reducing the measurement interdependency. So talking about variational quantum eigensolver using MBQC. So in a VQE, the Hamiltonian represents the energy of a quantum system. And there are poly matrices Z and X, which are fundamental operators in quantum mechanics, which represent the spin like head and tails and Blitz wave operations. And there is interaction ZO and Z1, which represents an interaction term between qubit 0 and 1, while X0 plus X1 applies single qubit operations. So what happens in a VQE circuit? In VQE, a parameterized quantum circuit is constructed to prepare a quantum state that minimizes the energy expectation value of H, and there is a parameter theta, which is introduced to vary the quantum state, like adjusting the angle at which a coin will flip. So there are also gate operations like Rx, Ry, and Rz, which are used for rotation around the X, Y, and Z axis of the Bloch sphere. And there is also entanglement, which is created by C0 gates, which is similar to flipping one coin in a way that influences the flip of another. So what is the purpose of this? That by adjusting the parameter theta, the circuit prepares the yield that will lower the energy value upon measurement, approximating the ground state energy of the Hamiltonian. And VQ uses quantum properties to potentially solve complex problems more efficiently than classical methods. So to conclude this topic, can you go on to the last slide, please? Yeah. So to conclude the topic, that advantages of using MBQC with graphic, it requires fewer gates and qubit compared to gate-based approaches. And it also achieves the computational efficiency using tensor network frameworks. And this work was done as a part of the Unitary Fund hackathon, where I was into the top 3 hackers worldwide. I actually solved around 6 issues across 5 projects. So that is about the project. And if you have any questions, then you can feel free to let me know. Yeah, thank you.
Great, super interesting work, Abdullah. And if you want, you can share your slide on Discord if it's available, because I think there will be many discussions about it and collaboration.
Sure, yeah.
Talk will then be given by Nigel. And you need to guide me through, Nigel, because...
Yes, just try to spend at most 5 seconds per slide, because there's about 30 slides there.
Perfect. Then...
Yeah, we're going to go really quick. So this is just like an overview of a previous presentation towards cybersecurity firm out in Korea. So it's just a background about who I am and my context to why I'm trying to use more advanced LLM models and get GAN models and overall just better AI, because we found its use cases to be very effective in protecting our cybersecurity, and also some references to previous projects too in certain use cases. And this is where it shines. The current state of our cybersecurity is not going to be the way it is currently. In the future, there'll be much more vulnerabilities. As I work in the realm of cybersecurity, with the things that we're doing now in quantum are opening the gates up for much more dangerous things to happen than things that are already happening. So I started a company out in Taiwan. I used to live out there, solving complex problems, working on AI speech to text. I was one of the earliest contributors to it, speech to text. Just a little bit of background. That's what I was doing then. Next slide. This is what I'm doing now. Next slide. Next slide. Next slide. Just a little bit of my background. So keep going. These were the most famous attacks of 2023. The French police were hacked. The United States military was hacked. Several other important people, key players that are protecting us, aren't meeting the demands of this quantum advantage, because while we're still trying to acknowledge that it exists, these communities, these niche communities, counterculture communities, are taking advantage of it. So you can keep going. Keep going. So this is like our key points to how we're going to address this that I've posed to that Korean firm last year. And those are the avenues that I highlighted during our private Zoom. So you keep going. Keep going. Just a different strategy. So now we're in autonomous AI now. So now we're in the realms of not just quantum, not just AI, but autonomous AI that acts omnipotently to some degree. These are the different key areas that it's affecting. Next slide. This is actually its practical implementations and my forecasting for where it's going to go in the future. As you can scroll down, you see future developments. This is just a short video of, next slide, short video of actually, who's familiar with Auto GPT. This is an example of it. You can kind of like just skim through. It's not a long video.
Chat GPT. Chat GPT. We're talking about Q in Auto GPT. Auto GPT.
Okay, so you understand that it has some degree of fear, and why there's a legit reason why we should all be at least paying attention to this. So that's just a little bit of my background. I was working on the speech text plugin and some use cases, but that was relevant for that time. Next slide. Keep going. You're almost at the end. Keep going. Keep going. Keep going. Keep going. Keep going. Keep going. These are just where it's going to affect the different fields, how we can address it. To keep going. Keep going. And now this is just like, so you can all type this in on your browser to kind of see like a use case of some multimodal AI if you guys haven't messed around with it. Go back just one slide. Right there, that's just explaining so now that I can't display this due to my my computer restraints, my hard drive space. So I recommend you guys go play with Hugging GPT so it can be used. Some of our previous presenters were talking about some of its applications and how we're improving our quantum models to address these issues with GPT. But keep going, keep going, keep going. We're at the end just about. And this is just this leads me to my project, my capstone, my project. Just last slide, like the slide before that. There's 3 slides back. And so my project is showing about how we can actually display the quantum advantage formally. Just the slide prior to that is a video. And I'll close on that. So right here, new applications and use cases. So now we can kind of use where we're going with quantum to kind of first address and solve. Some other members talked about some optimizations of models to address portfolio management, and of course reducing costs is another thing in depth as well. But this is kind of, if you press play on the video, you'll see just a preview of my my group project that we're working on. And first it's displaying the faults of quantum computing. It's also displaying I'm starting to display the quantum advantage, where we're halfway through the project and we're going to start to close it out by displaying how a 2D Trottenai circuit, as one of our previous presenters presented, can actually optimize our current classical models. So as you see, if you look at the metrics here, I've displayed the quantum advantage well above those 17 bits or 36 bits, right? We're at 200 and we're almost at 300 bits. And on my quantum neural network for my capstone with qubit by qubit, I was able to display some matplot library of the zeros and one states, and we were able to bring up the GPUs up to about 250 to 300 and 200, 300, 200 and 400 range. So we have displayed the quantum advantage. And as you can see, I have a little bit of gray hair here. I'm looking at myself. This has been a lot of work, but I'm looking to work with other groups. I've saw 2 to 3 key groups that can actually provide some breakthroughs in what we're working on as a whole community. So that's about the end. Thank you for your time.
Let me know if we can share the link to your website.
Yeah,
also.
more than welcome. You can share. Well, the Frame Tech Solutions is down. I'm no longer in Taiwan. I'm back home in the States, but you can definitely check me out on my GitHub. I'm on GitHub, swishcode, GitHub /swishcode. You can find me on LinkedIn at Nigel Phillips. I'm all more than open to solve some problems together.
Thank you all for today. This was an amazing session and look forward to seeing you Friday and to staying in touch. Thank you all.